In this video, we're going to talk about wavelength, frequency, and speed of light. Let's first start talking about wavelength. Let's imagine you are at the beach and there's all kinds of sand on the beach. And let's give yourself a nice big red beach umbrella. You are out in the ocean and you are watching the water waves come in and hit you and roll up onto shore. So the first thing we want to do is we want to measure the length of the waves, of the water waves that are coming in. So let's give you a very long meter stick. There's your meter stick. What we want to do is we want to measure the length of the waves. To find the length of the waves, we need to find the peaks in the waves, or similarly we can find the troughs in the waves, but the peaks are easier. So let's find a peak. There's a peak and there's a peak. So this is a peak, that's a peak. And what we want to do is we want to measure the distance between the peaks, and we call that the wavelength. So you have your meter stick here, and you measure with your meter stick, and let's just say you measure a distance of a ½ meter. That is the distance between two adjacent peaks in the wave. So now let's clean up our page and go on to frequency. So now let's talk about frequency. Instead of holding a meter stick in your hand this time, we're going to give you a big stopwatch. You got your 12, your 3, your 6, and your 9 on your stopwatch. And what you're going to do is you're going to press the stopwatch to start the stopwatch, and you're going to let the stopwatch go for a time of 1 minute. So let's say time is equal to 1 minute. And in that amount of time, I want you to clap. Keep clapping, counting the number of waves that hit you in 1 minute. So you press go on your stopwatch, and your goal is to count the number of waves that hit you. And let's say in a time of 1 minute, you counted 20 waves that hit you. So let's clean up our page. So in review, we measured the length of the waves and we obtained 1/2 meter. And then in 1 minute, we used our stopwatch and we counted 20 waves that hit us. And so now we want to find out what is the frequency. Frequency is given the letter F. Sometimes it's given the Greek symbol nu. And what it is the number that hit you over the time. So we clapped 20 times in a time of 1 minute. Therefore, the frequency is 20 claps or number per minute. Now let's do a conversion. Usually we have we convert from minutes into seconds. So we make our railroad track, we put minutes on the top and seconds on the bottom, and we do our conversion. In 1 minute, there is 60 seconds. So if we divide this out, we're going to get 20 over 60 seconds. So if we go to the next page, what we see is frequency is equal to 20 over 60 seconds, which is equal to 1/3 over a second. And this is equal to 1/3, and the unit is 1 over seconds, and that special unit of 1 over seconds is called a hertz. Hertz. HZ. So the frequency is 1/3 of a hertz. So let's do a review. So we counted the number of claps, that was 20. And the time was 60 seconds. The frequency is the number of claps per second, which is 1/3 of a hertz, or if you like real units, 1/3 1 over seconds as opposed to hertz units. And the wavelength is we measured as a ½ meter. So now we know what wavelength is and frequency. So let's go back and let's talk about speed of light. So before we talk about speed of light, let's talk about speed, because we really are not looking at light. We're looking at the speed of the water waves that are coming in. So there's a relationship between wavelength and frequency that equals speed. So wavelength times frequency is equal to c, or speed, is equal to speed of the wave. Speed of the wave. So, which we give the symbol or the letter v. So let's find the speed of the water wave. Speed of the water wave was the wavelength, which is 1/2 of a meter. And we're going to multiply that by 1/3 of 1/seconds. And what we get is 1/2 times 3 is 6. And then you have the meter on the top, and then you have the seconds on the bottom. And so the speed, or v, is equal to 1/3 meters per second. And if you want to make it a vector, then the vector means it's the number, the unit, and the direction, and we can say it's going in or towards the beach. So he gave it a direction. Now this was the speed of the water wave. So we looked at the wavelength of the water, and we looked at the frequency of the water hitting us in a minute, and then we calculated the speed of the water wave. Now how is this related to light? So let's go and take a look at light. So let's look at the speed of light. Still in the speed of light, we give it the letter c, speed of light. Wavelength is still going to have our lambda, our frequency will still be nu, and so speed of light, c, is going to be still equal to the wavelength multiplied by the frequency. So let's talk about light. So let's draw a picture of our sun. It's the way we see it, it is a yellow sun, so we'll draw it as a yellow sun. And it is shining in the sky, so let's put our ground here. So here's our ground. And you're standing here on the ground with your sunglasses on. And you are looking at the sunshine rays. So we have light rays that are coming in. These light rays that are coming in are in the wavelength band called visible. Because it's in the visible light, we can see it. So it's in the wavelength band of visible light. And the speed of light is exactly equal to 3.00 times 10 to the 8th meters per second. So that is the speed of light. So these light waves that are coming in, even though I drew them as straight lines or rays, they really are waves. So they are still the same shape of waves as the water waves. And still, the distance between the peak to peak is still the wavelength. And still, if you were standing here with a stopwatch and you counted the number that hit you in a time interval of a second, then what you would still get is frequency. Frequency is still equal to the number of those light rays that hit you in a time interval of 1 second. So when we look at the visible light spectrum itself, what we see is a rainbow of colors. So the rainbow is broken up into the red, orange, yellow, green, blue, indigo, violet. So I've shown these from left to right. The red block, the orange block, the yellow block, the green block, the blue block, indigo, and then the violet block. So that's your spectrum of light. If we were to draw this in terms of wavelength, we would draw a longer wave for the reds and then a shorter wave once we get down to the violets. And if you took a look at the length of the wave, for red, it would be much longer than the length of the wave for violet. So red wavelengths have long wavelengths, and violet wavelengths have short wavelengths. Now let's look at the values for wavelength. For red, you're looking at a value of somewhere around 700 nanometers. 700 nanometers, or 700 times 10 to the minus 9th meters, which means to move the decimal place 9 decimal places to the left. So that would be the same thing as 1, 2, 3, 4, 5, 6, 7 meters. 0.0000007 meters. So as you can see, the red wavelength is really small, but in the visible light spectrum, that's actually a very large number. Let's go to the violet side. The violet side has a value of around 400 nanometers, or 400 times 10 to the minus 9th meters, or that's likewise 0.0000004 meters. So the wavelength for the red is very long compared to the wavelength of the violet, which is very short. So where does visible light fit in this electromagnetic spectrum of light? So the visible wavelength band is actually a very, very small band. So there it is. It's a very, very small band in the electromagnetic spectrum. So the electromagnetic spectrum is the spectrum of light, is all the wavelength bands of light. So we have on the very one end, we've got radio waves. So we'll put radio in here. And then you've got infrared waves. You've got infrared waves, then the visible waves, and then you've got the ultraviolet rays, which I'll just give the little letters UV. And then you've got the X-rays. And then finally you have the gamma rays. So the visible band is a very, very small band in the very long band of electromagnetic spectrum of light. So let's start with the radio band. The radio band you're familiar with because it is the band that has the AM stations, the FM radio stations. So you're used to that as your cell phones are operating there. You can't see the waves that are coming to and from your radios and to and from your cell phones, but those are light waves, and those fit in the radio band. The infrared band, that band you're familiar with because it's the heat band. You may see, looks like you can see heat waves coming off the hot pavement, even though you can't see the waves. You're looking at the movement of air, but you get the idea of those are heat waves. You may feel the heat from the sun, but you can't see the heat coming from the sun. So you may stick your arms out on a nice hot sunny day and feel the heat. That's in the infrared band. Then you have the visible band, and notice that the red side, or the red color of the visible band, is on the infrared side, or on the radio side, which is the long wavelength side. So we can go ahead and label this side as the long wavelength side, or the short frequency side. More commonly referred to as the low frequency side. So let's label it as low. And then on the opposite end, we've got the short wavelengths, or the high frequency side. On the other side of the visible light, on the very right, or on the short wavelength side, you see the color violet. And that violet is on the ultraviolet side of the electromagnetic spectrum. So over in the ultraviolet range, you're used to these rays. Sometimes you get a sunburn, or sometimes you get a suntan. Those light rays that are coming from the sun that give you that sunburn and suntan are called ultraviolet rays. To the right of that is the X-ray band, which you're most familiar with is when if you go to the dentist and get your teeth X-rayed, or you go to the hospital and get your bones X-rayed. You can't see those waves, but those are in the X-ray wavelength band. And then the gamma rays are the highest energy rays, and usually they're associated with exploding stars. They'll emit lots of high energy rays, which are called gamma rays. And this constitutes your electromagnetic spectrum. Now, if you take any long wavelength from the radio band and multiply it by the low frequency of that same, associated with that same wavelength, the number of those same sized waves that hit you in a second, you would equal out and get the value of c, which is the speed of light. Or on the same thing on the short side, if you counted the number of gamma rays, if you were out in space and you had a bunch of gamma rays that hit you and you counted it, the number that hit you in a second, and you multiplied it by the length of the wave, you would still get the same value of c, which is 3.00 times 10 to the 8th meters per second, which is 3 with 8 zeros. 5, 6, 7, 8 meters per second, which is a very fast speed. And that concludes our tutorial here on electromagnetic spectrum, electromagnetic bands, the visible band, and wavelength, frequency, and the speed of light.